Hello everyone, Happy New Year and welcome to another video from series of solving a partial differential equation using numerical techniques. In this video we are going to solve 1D Poisson equation using both iterative technique and direct calculation by the using of the Jacobian matrix. So if you are interested, first of all do not forget to like the video, subscribe to the channel and press the rings to do not miss the upcoming videos. So let's start. Okay, we have one-dimensional Poisson equation, and because v is just a function of x, it should not be the partial derivative. It should be dv over dx squared equal to the f. Just a typo. Okay, let's continue. This is the derivative equation with known boundary condition. Value of v at the 0 point is v left, and the value of v at this point is v right, and we are going to solve this PDE in this one-dimensional area from 0 to d, and the boundary condition is known. Let's first solve this equation analytically. Okay, if we take the integrals from both sides, we will reach to this equation. dv over dx is equal to fx plus c1. c1 is some constant, and taking another integral, we will reach to the vx, that is 1 over 2 fx squared plus c1x plus c2. c1 and c2 is some constant. How we can find them? Just simply using boundary condition. At v naught, the value of v is v left. Therefore, 1 over 2 f0 plus 0 plus c2. It will give us c2, and this is v left. And we know that v at the point of d is v right. And just by substituting x to d, we will get to such an equation. All we need is to find c1, and after a little mess, you can easily see that c1 is v right minus v left divided by d minus fd divided by 2. So by just substituting c1 and c2 in this analytical solution that we got, it will be the final solution. Very easy. Let's move on. Now, what we want? Okay, we want to solve this equation numerical. We know that in finite difference technique, we divide the domain of the problem to some discrete points. Let's assume that we have 6 points, and we want we have 6 points. 1, 2, 3, 4, 5, 6. Okay, and we know the value of the v at the boundaries. Boundaries is v1 and v6. That's why I just color them with green, because we know them. And what we do not know is this red green dot, and we need to calculate this green dots using finite difference technique. From previous video, you know that definition of the second derivative is following: vi minus 1 minus 2vi plus vi plus 1 divided by delta x squared equal to fi. Just for simplicity, I define delta x with h. Okay, and if we gather all this value at one side of equation, we will get to such equations. And if we substitute, this is i1, i2, and let's substitute all I here, and we need to start from i2. Why? Because if we put I equal to 1, we will get v0 that does not exist. Therefore, by putting I equal to 2 until putting I equal to 5, we will get this 4 equations simply. And by changing I from 2 to 5, we will generate all v1, v2, v3, v4, v5, and v6. From boundary conditions, we know that v1 and v6 is known. H is some constant, and it is known. F is known. Therefore, let's just put all this known value at the right hand side of this system of equations. What we get is following system of equation. You can pause the video and just check every equation very simply. Therefore, this is the new system of equation. And if we write this system of equation in a matrix form, we will have such a equation. And you see that we have some matrix that is completely known. This element, all are numbers, right? And we have v here, and the right hand side matrix is again some known matrix. Therefore, what is unknown is this array, and how we can calculate it? Very simply, we see that this matrix M multiple to this matrix V is equal to this right hand side matrix, and V will be inverse of matrix M multiple to the right hand side. This method known as a direct method, or this matrix known as a Jacobian, so you can call it what you like, Jacobian method or direct calculation or inverse matrix method. And what does iterative technique says? Iterative technique says that if we keep Vi at one side of equation and gather all the rest at the right hand side, we will get such a equation in iterative method. And we see that Vi depends on the Vi minus 1 and Vi plus 1 and some known values. For example, the value of V at the grid point number 3, it's depends on 4 and depends on the value of function at the point 2. That's why we need to solve this equation inside the loop and just update. We will see it when we go to the Matlab. We will see it. Therefore, this is the equation for iterative technique, and this is the equation for direct calculation. Okay, let's go to the Matlab and start writing out the code. And that I have the written code here just for making video fast. I will explain every line by line. What does it mean? Okay, as usual, I will start with CLC, clear, and close out. Let's assume that, as we mentioned here, we have only six grid points for solving of this problem. Okay, therefore we define n, number of grid, with 6. D is some known value, just define everything that you like. And I define 12e minus 6. F again is some known value, just I define 1 in multiple to the 10 in power of 10, right? 1e10. We know that these two V left and V right again are some known value. I define it with minus half and minus 0.6, right? Okay, let's define x. By defining line space 0dn, you will indeed discretize this length with n number, right? With six number of grids. And what will be the h? H indeed is delta x. The difference between two grids is delta x or h, and this is d divided by n minus 1. Okay, let's check. When we have 6 number, just press F5. You see h is 2.4 in power of 10 to minus 6. Okay, just let me put semicolon here and continue. Now we want to have first the analytical solution. This equation is exactly the same that we derived here, and you can just easily compare half fx squared plus we write minus v left divided by d minus half fd multiple to the minus half f. Just a moment. Here we have the okay, yeah, here we are. It should be fd. Yeah, that's true. Minus f multiple to the d multiple to the half. Exactly the same. Multiple to the x plus v left. Just let's plot this va versus x. I just enable this all lines with Control T. Okay, plot x va with dotted line, and magenta is the color of line, and I define line width be equal to 2, and I just name x label with position, right? And I define just the unit with meter, and the potential is v, because when in the physics, when right hand side of Poisson equation is charge density, the unknown function that is v will be the potential. Great on, hold on. Let's just look at the analytical solution for, and you see here when the number of grids is 6, 1, 2, 3, 4, 5, 6. This is the exact solution of Poisson equation. Okay, let's move on, and we want to have Control T numerical solution using direct method. Therefore, okay, we need to calculate the v as we mentioned in that slide by just multiplying of some inverse of some matrix, multiple to the right hand side of equation. Therefore, first let's allocate some memory to the V, and this is possible by defining this zeros and 1. Okay, and again we know that V1 is known, and this is V left, and Vn, that here is V6, will be V right. Just okay, let's check, and by opening variable here we want to check V. You see that we assigned minus half, that is V left, to the first column, and we assigned V right to the last row, right? First row and last row, and all the rest is 0 because we defined 0 here. Just some definition. Now we need to define the matrix M. Okay, what we did indeed, we defined the matrix. We define this V. Let's define the matrix M, and you see that this is some diagonal matrix with the main diagonal and upper side diagonal and lower side diagonal is 1. Let's go just step by step how we can define. First of all, we see that when number of grids is 6, right? When number of grids is 6, the matrix is 4 by 4. Just count 1, 2, 3, 4, 1, 2, 3, 4. Okay. Therefore, this matrix, that is we defined zeros n minus 2, n minus 2. When we have 6 number of grids, matrix should be 4 by 4. When we have 10, 8 by 8. Just n minus 2 by n minus 2. Very easy. And what we see, we define right hand side. Let's define with some, again, matrix. You see that this right hand side is 1, 2, 3, 4. 4 by 1. Okay, therefore it should be 1, n minus 2, 1. And we multiply it with h square f that we have here. H square f is at every row we have this value, and because f is constant, all f2, f3, f4 and f5 is the same that we defined with f. But we see that at the first row we need to add v1, in that we subtract v1. At the last row we need to subtract the v6. How we can do that? Very simple. Okay, Control T. You see that I say that, okay, right hand side S1 is right hand side S1 minus V1. We can check. Just let me disable it with Control R and open right hand side. Just let me press F5. Okay, this right hand side is appeared. You see that this is 4 by 1, right? 4 by 1, and all element is the same, and this is 0.0576 as you see here. Just by adding V1 to the first cell and Vn to the last cell, just check. You see that the first cell and the last cell is changed, but the middle cells are constant. What else? Let's move on. Control T. This command TIC in the remember the time of starting of the calculation. By putting TIC here and TOC at the end of calculation, you can measure how much time does it takes to calculate everything. Okay, let's go again step by step. In previous video that you can find the link exactly here, I calculate the matrix M using some other methods, but here I am using some loops for calculating of this matrix. Okay, I'm just enabling this comment. Let's define a loop and change I from 2 till n minus 2. Just for a moment, let's disable this. And we see that the main diagonal of this matrix is minus 2, right? And if I define I from 1 to n minus 2, we can easily see that we put minus 2 at the main diagonal. Just let's see on the screen. Press F5, and if I open the M, you see all minus 2 is here, right? The next is just substitute 1 at this cell, and this cell, moreover here, here, and here. How? Okay, let's see. If I enable this command, I minus 1 is equal to 1. But we see that when I is 1, this will be 0. Therefore, we cannot put 1 here. We need to change this one to 2, right? It says that when I is 2, here M21 will be 1. M21 is here, right? Let's check. F5. Oh, sorry, M21 is here, right? 21, when I is 3, it will be 3, 2, 1, 2, 3, 2 here. And when I is 4, it will be 4, 3, 1, 1, 2, 3, 4, 1, 2, 3 here. And you see that by enabling this command or writing such a command, I minus 1 equal to 1, we can generate all these cells. But we missed this one. Why? Because we put n equal to 2. Therefore, I just add another command here. M11 should be minus 2. Okay? Therefore, first of all, I added minus 2 here. I create these cells. What I need to create these cells, right? What can I do? Okay, let's define again another loop. Okay, and change I from 1 to n minus 3. I plus 1. Mi. For example, when I is 1, it will give us 1, 2. Where is 1, 2? 1, 2 is here. It says that it should be 1. When n is 2, it will be 2, 3. 2, 3 is here. When it is 3, it will be 3, 4. And 3, 4 is here, right? That's why it should be from 1 to n minus 3. Why? Because we have I plus 1 here. And if this is n minus 2 plus 1, it will be n minus 1. n minus 1 is 5, and we don't have fifth element. That's why it should be n minus 3. By pressing F5 and updating matrix S, you see that I generate all element here at this matrix. Very simple. As I mentioned, there are some methods for defining of this matrix, but I highly recommend to, first of all, start with less number of grid, like 5, 6, 7, or 10, and you can easily check the matrix. And by defining several commands, you see that I generate this matrix. Now, just for checking, you can see that if I increase this 6 to 7, the matrix should be 5 by 5. Let's check. Yes, 5 by 5, and all elements are here, right? Just no matter if you change it to 200, we have the same. You see, all elements are here. One is here, one is here, and you can check just the last elements. And you see that we have exactly the same, minus 2, 1, 1, so on and so forth. Therefore, just for simplicity, start with less number of grid, like 6. And you can easily check everything to be sure that you don't have any mistake. Because if you start with the large matrix and just you forget to add some element, everything will be ruined. Okay, let's continue. Now, what we want to calculate the inverse of this matrix, right? And multiply it to the right hand side that we calculated here. And this is possible, Control T, this is possible by such a command, Control T. M / right hand side will give us the multiplication of inverse of matrix M multiple to the right hand side matrix, right? Simply. Why I call it with VC? Because you see that this M is 4 by 4, right? This is 4 by 4. This is 4 by 1, and this is 4 by 1. Therefore, you see that when this is 4 by 1, this is 4 by 4, the V will be 4 by 1. But we know that our V should be 6 by 1. But we know that, on the other hand, we know that the first element and the last element comes from boundary condition. That's why I save the multiplication of inverse of matrix M multiple to the right hand side with to the VC, and we can easily check. Let's look at the VC. It appeared here. You see this is 4 by 1 and all is saved here. What I need now, I need to give this VC to the previous v that I defined here with 0, and I give left boundary conditions and the right boundary condition to the first and the last cell, right? Therefore, what I need, if you check VC and V, all we need is just assigning of this VC, this element, exactly to the here. What do we need? Let's what do we need is just defining such a loop. You see, when we change I from 2 to n minus 1, vi equal to vci minus 1, and it will be done. How? Let's check. When I is 2, it says that give vc1 to the v2, vc1 to the v2, so on and so forth. When I is n minus 1, it says that gives vc, and we know that for simplicity we know that n is 6, n minus 1 will be 5. It says that when I is 5, give vc4 to the v5. What is vc4? vc4 here, v5 is here. Therefore, if I again update, you can see that v will be updated. Just press F5. Okay, you see that all these elements here just substituted to the here, and we updated the v. We have the solution now. Just let's again plot this v and see how does it look like. Control T. This is plot xv with blue line, with blue dashed line, and this O means the marker is O. Very simple. And just I am defining a legend. The first graph is exact solution that we find from analytical solution. The second graph is direct method, and just some grid on. Let's look, and you can easily see that both graphs are coincide on each other, exact solution and direct method, just by several very simple command. Now, okay, now that we found the solution, let's check the error. I defined ED, okay? I defined ED with the absolute difference between analytical solution and numerical solution using direct method. And just be careful, guys. We found VE, VA here. Let's look at the VA. VA is following. You see that this is a row matrix, right? There is 1 row and 6 columns. But what is V? In the V there is 1 column and 6 row. Just by putting some dot here, you see, I here calculate the absolute of VA minus V, but here you see a dot, a comma. This dot comma change a row matrix to the column and vice versa, columns matrix to the row. Therefore, if you do not put this dot comma, the error will appear strange. Okay, just another figure. Plot X error D with blue line. X label position, Y label is error, and grid on. Let's see. You see, this is the error. And just for checking, let me clear this dot comma. You see how does it look like? You see, this is a mess because one is 1 by 6, the other is 6 by 1, and when it subtract these two matrices with each other, it gives you 6 by 6 matrix, and easily you can see here that and this is wrong. You see, this is wrong. Therefore, just put dot comma, and it gives you the error here. Updated. It is updated, and just let me close this, and error is error D. And you see that error, the maximum of error, and easily we can see here is in the order of 10 in power of minus 16. Okay, let's increase the number of grid. Now we see that when number of grids is 6, error is in the order of 10 to minus 16, right? Let's increase it to 20. How much is the error? The absolute error is about 10 to minus 15. 50. Again, 10 to minus 15, the maximum of error. For example, 100 minus 14 500 minus 13, 600 minus 13, 700 minus 13. You see that error, although slightly increased, but by increasing of the number of grids, this error tends to some constant value. You can easily check it by yourself just by defining some loop and changing the n from low value to the large value, and you can easily do this. And when n is 1000, it's again roughly 10 to minus 13. Let's check 2000. Again, minus 12, 4000, minus 12, 6000. It takes time. You see, the calculation takes time, and it took 3.3 seconds. You see that, by the way, it tends to some 10 to minus 12, right? And the absolute error is not greater than this error, and this is quite acceptable. The difference between the exact solution and the numerical solution is in the order of 10 to minus 12, and you easily can see here how they are coincide on each other. Just I decrease it to 100, and you see how much is this? They are fitted to each other very well, right? Okay, let's continue. I again decrease number of grid to 6 and go on to the iterative technique. Control T. Numerical solution using iterative method. Control T. Control T. Okay, let's again allocate a memory to the V. I just define this V here. This V with VI, and I here represent the iterative technique. VI means that we have the solution of V using iterative technique. Therefore, again, the V should be zeros and 1. Dimension should be 6 by 1. I will explain about this slide later. Let's go on. Define the right hand side. I define right hand side with some unitary matrix, 1's n 1f multiple to the f. Let me show you here. Yeah, this is indeed the f. Just f, because I will multiple this h later. This is right hand side, and or you do not define this right hand side and just define here, but no matter. And Control T, VI1 is V left boundary condition, left boundary condition, and right boundary condition, VIN is V right, like previous. About iteration error, I will explain later. About this, explain later. This, let's skip this. Control T, TIC again. Well, remember the time of starting of the calculation, and this TOC will remember the end of time of calculation, and by subtracting this to value, it gives you the times that takes for calculation, like previous one. Okay, what I need, let's define a loop, Control T, and we say that change I from 2 to n minus 1, and this is the exactly the same equation that we derive here. You see, Vi is half Vi minus 1 plus Vi plus 1 minus h squared Fi, that is right hand side in definition, in this definition, right? Right hand side is just f. Why I just do not use this constant value? Because sometimes this n function is not constant, right? That's why I allocate an array instead of a scalar value. Therefore, if your f is some equation, not constant value, you have to have the same value of f at each point. Okay. Okay. Therefore, we calculate Vi here. Just let's look at the appearance of the solution of this Vi. Control T, another figure, plot x. No, this is analytical solution. Let me just disable this. Oh, okay, let's have this. This is again analytical solution versus x, and x is x label V. Okay, just hold on and Control T. plot x vi with red dashed line and O marker, and legend exact solution, iterative method. Just let's look at the solution. How does it looks like? You see, this is the exact solution, and this is the solution that we found using iterative technique. But we do not use iteration here. We just calculate value of v at each point based on this initial guess that we assume that this is 0, right? But this initial guess is not true. This is just guess. We need to use iteration and make the solution close and close to the real value. What we need to do, just define another loop by like this. For k1, 2, for example, any number, just repeat this solution, right? Repeat this value, because when we update, we calculate vi here, we also found vi1 and vi minus 1, right? Just let's look at the solution. How does it look like when the iteration number is 20? We just calculate this equation 20 times inside the loop. Pressing F5. You see how this iterative method tends to the exact solution. Just let me reduce it to 2 from just twice. Calculation it twice, you see. 3. Let's look at the solution. Okay, it is not true again. 10. You see, after 10 iteration, it tends to the exact solution. 20. 20. If we look at this, we say that, okay, 20 iteration is enough and the solution is exact. No. What we need, let's again calculate the error. And the absolute error is the difference of the exact solution and numerical solution using iterative technique. Just I enable this command again using Ctrl T. Therefore, I define error iteration with absolute of VA minus VI. And this dot comma is for the same reason that I mentioned. Okay, another figure, plot X error iteration with red color. Okay, let's look at the error when the number of iteration is 20. You see, the absolute error is in the order of 10 minus 4, but in direct calculation, what we found, it is in the order of 10 minus 16. Very different, very different. Although appearance is the same at the first glance. This is exactly the same that we have here, but no. You need to look at the error. Here error is quite low, but here error is considerable. Okay, what we need to increase the iteration. But how much we need to increase the iteration? You may say that, okay, we have the analytical solution. We can define some error, and we can say that when this error is less than some acceptable number, we stop the iteration here. But in real problem, we do not know the analytical solution. We are using numerical solution for the problems that we can't have the analytical solution. What we can do for this? Okay, let's do following. Here, let me define some vi old. Here, I defining some vi old that is equal to vi. Okay, some value. Then after this loop, you see that the vi is updated, right? And let me just define some iteration tolerance, Ctrl T. Let me define some iteration tolerance by the absolute of vi minus vi old. Here we have vi old, here vi is updated. Here vi old indeed is vi, but after updating of vi, they should be different. And I save this difference to this iteration tolerance. But I need to save all the difference of vi and vi old at all the 6 points. Therefore, here I need to define some matrix. Iteration tolerance 1 and 1. It says that it will be 6, 1, right? And it will save the difference of vi and vi old at each grid points. Okay, let's see. You see that I want to show you this iteration error, iteration tolerance. You see we have 6 points and we see the tolerance at each point. How much is this tolerance? Now, okay, now we have some gauge. What is this gauge? We say that, okay, instead of using this for loop, let's disable this, Control R, and enable this Control T, Control T, Control T. Okay. I want to say that when the maximum of this iteration tolerance that we are calculating here is greater than some value, just continue this loop. But as soon as this maximum of iteration tolerance is less than this value, it will stop the calculation. Okay? It will stop the calculation. And let's define this value as some small number, for example, 1 to minus, for example, 3. Okay, if we look at the iteration tolerance, we say that when continue this loop, while this maximum iteration tolerance is greater than 1 in minus 0, and if you look at the iteration tolerance, all value is less than this number, right? And it stops at this point. Okay, let's increase this, for example, minus how much? 7. You see, this tolerance decrease. What does it mean? It means that we have some VOLT, we have some initial guess, we assign this initial guess and calculate VI using this initial guess. And after this calculation, we update this initial guess from the previous solution at the previous iteration. You see, we give VI to the VOLT and we update this VOLT. This should lead to some convergence. It means that this VI old, that is somehow is our initial guess, tends to the exact solution by increasing of the iteration. And we can easily check it, how this convergence happen and how this VOLT tends to the exact solution or VI tends to the exact solution. Okay, let me define some iteration number here. Iteration number. I say that iteration number is 0 just before starting of this while loop. And at each iteration, I added 1 to this number. Therefore, just count the iteration number. And I save this iteration number to some matrix. Iteration, right? Iteration. I define it with iteration, and this index iteration I shows indeed the number of cells of this iteration. We can easily check it. Just press F5. If you look at the iteration, where is the iteration here? Iteration. You see that this is 1, 2, 3, 4 until how much? 37. It means that it took 37 iteration to the tolerance be less than this number, right? It's continue this loop while maximum of iteration tolerance is greater than, and it will stop when the maximum of iteration tolerance is less than 1 in minus 7, right? And Control T, and I save the maximum of iteration tolerance. I just save the maximum of this iteration tolerance to some number, to some array, and this array is tolerance max, and the index is iteration number. You see that this the circle is yellow because we did not allocate any memory for the iteration and tol underline max here. And if we define this this matrices here, iteration is zeros, just some parentheses without any number, because we don't know what will be the final iteration number and what will be the final iteration tolerance. That's why when we define like this, it's some open memory that will increase by increasing of the number of iteration, and the size of this iteration and toleration max, it is not defined first, but you see that by such a definition the circle becomes 0 because we allocated some memory to the iteration and tol underline max, that just we save the maximum of iteration tolerance to this array, and it's become you see green. Now what we can do, okay, we have everything. We have the analytical solution, we have the direct calculation, we have the numerical solution using direct calculation, we have the error, that is difference between analytical solution and the direct calculation. Again, we have the exact solution and a numerical solution using iterative technique, and we have the same error just by comparing exact solution and numerical solution. And as I mentioned, we cannot have the analytical solution in real problems. That's why let's look at this maximum of iteration tolerance. How does it looks like? Okay, just again I define this comments, Control T, again a figure, new figure, and I plot maximum of iteration tolerance, that is I define with tool underline max, and plot it versus iteration, that is indeed iteration number. Just with red, line width is 1.5, grid on, and I just set the x and y value with a logarithmic scale by using this command, set GCA, y scale, log, you see, and x label is iteration number, and y label is maximum of tolerance. Let's look how does it looks like when I says that, okay, stop this loop when iteration number is less than 1e minus 7, F5. You see, this is how the problem converges to the real value that I showed you. Because when the number of iteration is low, we have such a tolerance. For example, here when number of iteration is 10, the tolerance is this number. But when number of iteration is 20, the tolerance is this. We can define some tolerance. And just for comparison, you see that when the tolerance, we define tolerance to be in the order of 1e minus 7, you see how much is error? It's about 10 to minus 7. Therefore, we want to make it as close as to the direct calculation, 10 to minus 16. Let's put it 10 to minus 16 and press F5. You see, it reached to the 10 to minus 16 after how many iteration? After 86 iteration, it reaches to the same tolerance that we defined. Therefore, if you look at the error is about the same as that we have in the direct calculation, very easily, right? Very astonishing. Okay, what I want to show you, okay, just let's decrease it slightly to be fast, because if just look at the time of calculation, you see the time of calculation for direct method is this value, and in iterative method is this value, and you see that iteration method is about 10 times slower than the direct calculation. But we need somehow this this iterative calculation, and it will be the topic of next video that I will show how we can solve a nonlinear Poisson equation using iterative technique. That's why, although it takes more time, but sometimes we have to use this iteration technique. Okay, just let's increase the number of grids, for example, to 15. 15, press F5. Okay, you see how this problem converges to the real value, to the exact solution, like this. And this is the error for iterative technique, right? This is the exact solution and solution of numerical method using iterative method. Error of direct calculation using Jacobian matrix, and this is the exact solution and direct method solution. Just I want to show you something more. Let me disable all the figures. Control R. By Control R, we have a figure here. What else? Another figure we have here. Control R. Another figure we have here. Control R, and another is here. Control R. And let me disable this command and put a hold on here. I want to show you how the convergence looks like. I mean, how the convergence appearance is when the initial guess is something different. We say that at this calculation, initially we say that, let's say that the initial guess is 0. We assume that the potential is 0 everywhere. Just let's use another initial guess, Control T, Control T. This is what it says that, let me disable this, Control R. It says that when x is 0, vi is v left, and when x is d, vi is v right. When this is d, it will be 1, this cancel this, and there vi will be I will be v right, that is right boundary condition. Just before all of that, let's just look at the appearance of the initial guess. How? Just okay, if I enable this comment, no, this comment, okay, Control T. Now let's look how this initial guess appears. Okay, and what we need is just enable all of this updating of the VI and press F5. Okay, where is it? Figure 2, exact solution. Something is wrong, I think. It's VI. I just disabled it. All of this calculation, VI. Let me just disable this analytical solution and look at the initial guess. VI. Okay, let's do following. Let's disable all the rest comments and just copy this plot from here to the exactly here and see how does it look like, and disable all of this. Control R. This is indeed initial guess. This is some second initial guess for VI. Let's look at the VI. You see that it's linearly changed. This is indeed our initial solution, initial guess. Just comparing with exact solution, let me enable this. Control T, Control T, Control T, and put a hold on here. Hold on. What is the problem? Oh, hold on. Oh, I need to disable also this one, controller. Okay, this is indeed exact solution, and this is the second initial guess that we defined. Just linearly change between the left boundary condition and right boundary condition. First, we saw everything with this such an initial solution that is 0. Control T, Control R, and just Control C. Let me put the boundary condition also here. Control T. We have two initial solutions. One is this is 0. This is our first initial solution. This is the exact solution. This is the first our initial solution. And we have another Control R, Control E, and we have another initial solution that is linearly changed between left and right boundary condition, F5. This is the second initial solution. I want to show you how the initial solution can affect the convergence of the problem. Therefore, let me disable this close out, Control T, Control R. Okay. close all, VLC, clear, VLC. Okay, I cleared everything and I just want to have the convergence of the convergence graph. Therefore, I need to disable this, Control R. What else? I need to enable this one, Control T. Okay. Now we have second initial guess, F5. What is the problem? Iteration. Undefined iteration. Oh, sorry. I need also to enable all of this. Control T. Okay. Again, I do not see any graph. Control R. Max of tolerance. Why this is not? Can see anything. Okay. Oh, why this is disabled? Control T. Control R again. Okay. This is the appearance of convergence for the second initial guess. I want to also keep this and calculate convergence with the first initial guess. Control T, Control R. Okay, Control R. With such initial guess that is linearly changed between left and boundary condition, and press F5, I will have the graph on the same with blue color. You see, when we have a better initial guess, the convergence is slightly faster. For example, here we see that with 1000 iteration, about 1000 iteration, the error is less for the second initial guess in comparison to the first initial guess. That's it. And what I mean is that try to have better initial guess in using of a iteration techniques, and easily you can see here that with the better initial guess, the convergence will be slightly faster. And that's it. Okay. By the way, I'm keeping the first initial guess, Control R, Control T, and let me enable everything and sweep this, and you can pause the video and check every line just for the last time. Control T, and it will be the last version of code. Control T, Control T, Control T. We don't need this plotting and hold on here, just I'm deleting it, and I want to delete this. Okay, it was what else? Control T, Control T, Control T. We don't need this hold on. Control on. Okay, the number of grid is 50. Let's just check everything. Press F5. Yeah, everything is okay. This is the direct method exact solution, error of direct method, iterative method and exact solution, error of iterative method, and this is the convergence. And this is the, okay, just want to close this, and this is the last version of the code. I'm just slightly sweeping to allow you to check every line. By pausing out the video, you'll see every comments here, how does they defined. Okay, and yes, and yeah, that's the end. Thanks for the watching, and if you like the video, please do not to like the video and subscribe the channel. Goodbye.